Let us continue our discussion on mode curve analysis. Let us look at the mode curves. This graph may look difficult to understand, but let us first focus on the lower portion of this graph. So this is the lower portion of the graph. This is the upper portion of the graph. Let us look at the lower portion of the graph. Lower graph, if you look at it, the x-axis is reflector voltage, which is given in volts, and y-axis is power of the microwave signal, which is in milliwatts. Okay, so you have voltage, reflector voltage on x-axis, and you have power in milliwatts on the y-axis. So I have given some example values on x and y-axis to give you an idea. Remember, for the microwave signal to be useful for any application, we need two important parameters. So we have discussed this before. So for any application, the oscillator output, we are interested in two parameters. One is the frequency of the microwave signal. Second is the power of the microwave signal. Reflector voltage, as we know, has negative polarity. So reflector voltage has negative polarity, and hence it is shown here as all negative values. See, this is minus 750, this is minus 500, and this is minus 100. By increasing the reflector voltage, which means by making the reflector voltage more negative, the electrons are reflected with greater force, and hence they spend less time in reflector space. Okay, so if you see here, if the voltage is more, like for example V1, okay, so V1 is, here is the reflector electrode. So if the voltage is more, the electrons travel less distance in the reflector space and they quickly reflect. If the voltage is less, these electrons travel deeper into the reflector space and then reflect back. Okay, so if the voltage is less, they go deeper into the reflector space. If the voltage is more, they will be pushed very soon to go back. Okay, and this is how the bunching happens. This implies more microwave signal power in less time. Okay, so we get more microwave signal if the reflector voltage is more. By decreasing the reflector voltage, which means making the reflector voltage less negative, the electrons go deeper into the reflector space. That is what we shown here. So now let me go to the next slide. Let us continue our discussion on the lower graph. So look at the graph from left to right. Okay, so look at the graph like this, left to right. Now clearly modes have lower modes, right? This is a lower mode. This is n is equal to 3 by 4. This n is equal to 1/3. This n is equal to 2/3. So the lower modes have higher output power. So this is a lower mode, n is equal to 3 by 4, but the power is higher. See here, the power is higher. So if you take n3 by 4, then the power is 1000 milliwatt. Okay, 1000 milliwatt is equal to 1 watt of output power. Now if you look at a mode which is a higher mode, n is equal to 2 3 by 4, then the power is, this is the power, which is 250 milliwatt or 0.25 watt. So this was explained in the previous slide, where we saw that higher reflected voltage implies more bunching. So in the previous slide we saw that if the reflector voltage is more, then the electrons will be reflected faster and the bunching happens faster. That means the power is more. Okay. So thus it requires less number of cycles. So it requires less number of cycles for the bunching to occur. Okay. So that is the theory. Okay. This is about the lower graph. Now let us move and analyze the upper graph. So this is the upper graph. Here x-axis is same, which is the reflector voltage, and y-axis is frequency deviation, which is expressed in megahertz. So what is frequency deviation? Let us recall that the cavity in a reflex klystron is similar to a tuned LC tank circuit in electrical sense. This means that the center frequency is decided by the cavity. So this is the center frequency, 10 gigahertz. This is the frequency of the oscillator, and this is decided by the cavity dimensions. Okay. We are not varying the cavity dimensions. We are only varying the reflector voltage. But in reality, what happens is we cannot design something which is perfect, and we cannot get an exact center frequency, nor can the system maintain the frequency exactly as it was designed for. So what this means is, if the cavity dimensions are designed for 10 gigahertz, it is impossible to get exactly 10 gigahertz. There will be some variation from 10 gigahertz, which is plus or minus frequency deviation. So let us look at this picture. So if green color represents the exact frequency which we designed it for, let's say FC, then all these are the frequency deviation values from the center frequency. So the red lines represent deviation from the center frequency on the higher side. That means this is FC plus FD, and the red lines on the left side represent FC minus FD. So as you can see from the upper graph, as the reflector voltage increases, so as the reflector voltage increases, minus 750, for example 750 volts, it's a higher reflector voltage, then we can see that the deviation is lower. See, this is the deviation. Deviation is from minus 5 megahertz to plus 5 megahertz for minus 750. Similarly, if the reflector voltage is reduced, so if you reduce from minus 750 to minus 100, then the deviation increases. So if you reduce the voltage from minus 750 to minus 100, you can see that the deviation increases. So now the deviation is from minus 10 to plus 10 megahertz. Okay, so this also depends on the mode. The frequency deviation may be acceptable or not depending on the application. So some application needs the oscillator to have different frequencies and wider deviation, and that helps so that we can tune the system to required frequencies. So finally, about the modes of operation. So in the practical klystrons, the values of n range from 1 3/4 to 10 3/4 cycles. That means the practical klystrons are in these ranges. Okay, this is 1 3/4, it is 2 3/4, and so on.